Welcome to our second edition of use cases from the EOSC community. My name is Alexandra Singer. I'm from EOSC Future. Today we will hear 9 presentations, and these are from research teams in EOSC Future, C-Scale DICE, EGI-ACE, OpenAIRE Nexus, and Reliance. All these projects, whether in climate and environmental science, or smart cities, astrophysics, the social sciences, and biomedicine, all of them are using EOSC tools and services. So today we'll have the chance to see EOSC in action in a variety of domains and in different countries. Before we start, I just want to do a bit of housekeeping. So we'll be recording this session. So all the video and the presentations along with the demos will be available on the EOSC Future website after the event. You'll get an email about it, but we'll also post it on the website. And please feel free to ask your questions directly in the chat. What we'll do is after each of the presentations, there will be 5 minutes or so to ask those questions. So we'll collect them and then we'll present them. And with that, I'll hand it over to our first presentation from the EOSC Future project. So that's Hilde Orten, and she's a senior advisor at SIC, the Norwegian Agency for Shared Services in Education and Research. So take it away.
Hello, and thank you very much for your introduction. I'm going to talk about our EOSC Future science project, Climate Neutral and Smart Cities. And that is basically very much about integrating data from different clusters. And EOSC Future has allowed us to collaborate across clusters with ENRI and ESHOC together. And that is an opportunity that we wouldn't definitely not have had if it wasn't for EOSC Future. So what is the objectives of this project? It is first and foremost to demonstrate that relevant environmental data and data on citizens' values, attitudes, behaviors, and involvement can be combined for social, political, and scientific analysis. And second, data will be available from the EOSC platform. As I said already, this is a cross-cluster project with ESHOC represented by European Social Survey, ERIC, by the City University of London, and us at SICT, which is the data archive of the European Social Survey for 20 years, by SESTA, the Swedish National Data Service, and from the ENRI community, we have IAGOS, and also project-independent experts from the meteorological sciences and air quality sciences have been helping us with the project. So what is the problem? On a very high level, it is about man in his or her environmental context. And more specifically for this project, do observable indicators related to climate change or local air pollution have effect on climate change, on attitudes to climate change, or effect on well-being indicators? On the picture, you can see a person being interviewed, and he is asked the question if he thinks the world's climate is changing. And you see the temperature is very warm, it is sunny. Would this have effect on the response? Would environmental factors in the near term before the interview have effect, like 1 week before, 1 month before? How was the environmental indicators in the year before? How was it compared to normals, and so on? This science project rests on 3 pillars, and all are important. One is indicator production and data integration. And this is to combine the survey data with the climate data and air quality data and compute useful indicators for analysis. And that is not really something you can do right away. This requires a collaboration between experts in different fields. We need to understand each other and we need to use each other's method. And this has been done for this project. We produced like almost 60 different indicators from a set of basic variables from those sciences. And it is also about cross-domain metadata. How can data from those sciences be integrated? So we will be using a standard called a DDI cross-domain integration for the provenance part, and also combined with the domain standard for the social sciences called DDI lifecycle, which is a structural standard on a very high level of granularity. And dissemination is also important. We are developing at SICT an ESS context lab prototype, and this will be available as a service from the EOSC portal. And here we have basically a picture of what we try to do. We have climate data from ERA 5 that are variables available in NetCDF on a very high level of granularity when it comes to the geography and time also. We have air quality data from the European Environmental Agency, and we have survey data from the European Social Survey. We do integrate indicator production, and then we integrate the data. And here you can see an example of one of the indicators that we have. We are focusing on what happens on a specific date. And like here, this variable about the worst air quality index level of PM10 at that date. And we do that for a set of classical air quality indicators. So the more classical pollutants like PM10, PM2.5, SO2, NO2, and O3. And then we do it across pollutants and on region and so on. And it's very important when you do things like this and work together that everything you do is transparent. Therefore, we also will make available the computation rules for the things we do, both in a human readable manner like here, and also the code. And we are doing cross-domain metadata, and it's very important when you're doing cross-domain and really cluster things that you document everything you do. And we will do this using a machine-readable tool that we are developing, where all the steps and on a very detailed level, what happens will be documented. So we have a higher level step, and then we have sub-steps of that, and then we have in and out parameters from those steps. We have this down to the variable level. And here you can see an example of the tool we are developing. This is a prototype. We start with the highest level steps, and then we go down to what happened at each kind of data set that we are doing. We get, for example, from the ERA 5 reanalysis data, we get raw input, we are marshalling data, we are processing data, and the same with the EIA air quality. And then in the end, we merge them with the ESS data. So you can see here under data processing, we are creating variables like the one I just showed on the indicator level. And in this tool, we will include the variable and also link to all the input variables that it takes to create this variable, and also the output. And we will have a Python script and a human readable description for everything. And then when you go to the output variable, it will take you to a page that explains more about the variable and the codes and the description and otherwise information about that variable. So metadata, as we all know, is allowing reuse and reproducibility, and especially if it is on a granular level, it is very good for that. Therefore, we are exploring possibilities for the new DDI cross-domain integration standard DDI-CDI. The provenance part, I already showed you a little about what that can do. And this standard can also describe data from different structures. So if you structure it in a specific form that it has originally, you can really have the metadata follow when you transform it into different structures and so on. We will not do that in this project, but we will describe the possibilities that this option can offer. Also, you have to deal with catalogs details, how it is the best way to do that. Is it together with another standard, or what should you use, and so on. And we will explore and use together with DDI lifecycle, and we will describe how that can be done also. And then for dissemination, this is my final slide. There we are creating the ESS Labs, which is a prototype application with this project as its first instance. And that is starting from ESS data portal technology that is already out there. And we will add DDI-CDI based provenance components. We will develop further the tool I just showed to you, and then make everything available from the EOS portal, and add ESS Labs as a survey, and the European Social Survey is already onboarded. And just to finish off, I can say that I presented this in different settings, for example, at the EGU 2023, and I got lots of interest in the project, and also for this kind of cross-cluster collaborations. So if anyone else are interested, just get in touch with me, because I think this is things like this, and working together on a very basic and detailed level like this is really what it requires to take cross-domain research forward. So these are people that have been working on the project. So thanks to all of those. And we are looking forward to mid-September, when we will all get together in Madrid to present the results of our project. And thank you very much for this opportunity, and thank you to the EOSC project lead for organizing and helping us out so much that they have done with this project. So thanks, and questions?
Thank you very much, Hilde. I don't see anything in the chat, but if anyone wants to raise their hand, ask a question, feel free. Okay, maybe we can ask more questions after the next presentation. Next up, we're going to be hearing from Escape Gravitational Waves. We'll have Dr. Danny Vol from the University of Amsterdam and Astron in the Netherlands, from the Scuola Normale Superiore Analysis.
Good morning, everyone. Let me please share my screen. There we go. Oops. Take a second. Okay. Well, thanks for having me, first of all. So today I'm here to present our test science project as part of the EOSC Future conglomerate, I suppose. So this talk is on behalf of everyone that works on the compact object test science project as part of the gravitational wave work package. And so EOSC Future has been quite useful in our case to access both compute resources and storage which is somewhat of a limitation when it comes to astrophysical data sets that can grow quite quickly, and they tend to be quite large data sets and heterogeneous. And so it's nice to have the EOSC Future infrastructure to gain access to a vast number of catalogs, for example, and resources such as the data lake. And so just to make a quick picture of why what we're trying to achieve with our research projects, our project is related to the search for fast radio bursts. So what are fast radio bursts in the first place? So these were first discovered in 2007 in archival data from a telescope in Australia, while people were looking for further away pulsars than what had been known so far. So most pulsars to date, so pulsars are the left dense core after a star has exploded at the end of its life. And so we have a number of pulsars within our galaxy that are being used for a number of different purposes, such as measuring the number of electrons within our galaxy, for example, or nowadays they're also used as a probe for gravitational wave because they're very precise clocks. And so people were looking for pulsars in other galaxies, essentially. And then by looking at archival data, they found these highly dispersed pulses. So here we can see a plot here of the frequencies versus time. And the dispersion measure here so that's how we call this. This is related to the fact that these pulses are going through space, and as they go through space, they interact with the matter. So the electrons that are within our galaxy, for example, or in between stars and so on. And so when they get emitted from the star, all the wavelengths are at the same frequency. But as they travel, the higher frequencies will keep on going faster, and then the lower frequencies will get delayed. And so this has this specific quadratic sweep that we can see here, where the higher frequencies arrive earlier at the telescope, and then the lower frequencies arrive a bit later. And for pulsars, this was already known that this was happening, but the dispersion measures seen for pulsars tend to be much smaller than this. So generally, pulsars will be found in this window here, which corresponds to what the amount of electrons within our galaxy, essentially. But these pulsars, or these pulses, were found to be much more dispersed than the pulsars, and therefore were thought to be extragalactic. And so this represented a new probe for studying the universe, essentially. And because they're so much more dispersed, we think that the luminosity has to be orders of magnitude greater than what is seen in pulsars. And so nowadays, one of the questions is what is actually emitting these bright radio pulses? And so by doing so, people have continued to monitor these sources, and eventually some sources were found to be repeating. And so the fact that they were repeating allowed us to actually pinpoint on the sky where the source was located. And so, for example, here, one source was localized to a dwarf galaxy that we can see here in the little blue picture here. And not only did we get these millisecond flashes of radio light, but there was also a continuous source that was found at the location of this specific fast radio burst source, called a persistent radio source, that was too luminous to be explained purely by star formation in the galaxy. And so follow-up observing with the Hubble Space Telescope showed that both the persistent radio source and the fast radio burst were as part of a knot of star formation within that dwarf galaxy. And then further observations in the radio band at very high resolution. So if we zoom in into this point here, we can see that both the FRBs shown by these little crosses and the persistent radio source, this little yellow blob here, were co-localized to within 40 parsec of each other. So they're almost at the same place on the sky. And so somehow these two phenomena are related. And further properties of the source, such as the fact that the spectral index is almost flat. So if we look at it at various frequencies, we see that we get almost the same flux, essentially. There's also a high variable rotation measure of the polarization of the light. There's been secular changes that's been measured for the dispersion measure. So total amount of electrons that's been visited by this pulse, essentially. And the spectral energy distribution that you can see here. So how much light you get at various frequencies, going from radio to X-rays. Somewhat follows what is seen for a pulsar nebulae called the Crab nebulae, although orders of magnitude more luminous in this case. And so all of these kind of argued for the fact that we're looking at a very young, highly magnetized neutron star that would still be within the cocoon of the explosion that happened a couple of years ago, essentially. Another explanation would be that this is a low luminosity massive black hole that is accreting matter and therefore might be luminous, but the mass that was inferred was about the same as the mass of the galaxy itself, and so it's a bit hard to reconcile. But nevertheless, we're gathering more and more information since 2007 to make to understand what are these sources. And in the meantime, people have also been looking to find black holes in dwarf galaxies. So they've been theorized to be potentially found in these, so intermediate mass black holes. So we know of stellar mass black holes. We know of supermassive black holes like the ones we have in our Milky Way. But there's this in-between mass range that is still a bit elusive. And so people have been trying to find these intermediate mass black holes. And it's been shown that a couple of these candidates that were found in dwarf galaxies show similarities to these persistent radio sources that I've just been talking about. And so we might actually be looking at similar phenomenon here. And therefore, if we actually manage to find some, we might hit one bird with two stones, as they say in English, I think. And so we've been, within this project, we've been trying to find more of these persistent radio sources in large catalogs. And so that's how we've been using EOSC. Essentially EOSC Future. We've been searching the LOFAR 2-meter sky survey, which is a survey with the LOFAR telescope, which is a European wide radio telescope. So it's an array of low frequencies antennas that has the core of the observatory within the Netherlands, but with stations going all around Europe, all the way to well, from Ireland to Poland and so on. So it's a very much like a scattered array of radio antennas that can be all being used together to survey the sky. And so here we can see what has been observed so far. So all the green region here is what the LUT survey has been covered so far of the northern sky. And we've been cross-matching that survey with a number of other catalogs in the infrastructure to try to pinpoint some of these sources. And so we now have a number of candidates that we've been identifying, and now we're following these up with more data coming from both the virtual observatory and various catalogs and gathering more information. And so, yeah, EOSC Future has been quite practical to access remote compute for both our team and also to teach students, for example, bachelor students that work with us. We've gotten great help by the technical team. So, for example, thanks to Elena Gazzarneri, Enrique, and Jan Grange, for example, at Astron. That's been helping a lot. And also the discoverability and the interconnection of the services and so on that are found now on the marketplace of EOSC Future. And I'll keep it at that. I think I might have gone a bit too long already. Thank you. If there are any questions, please feel free to ask, obviously.
Oh,
yeah. There you go.
Okay, great. Thanks. I think Alberto will go directly to you, and then afterwards,
yes.
we can have Q&A for all the participants.
Yes. So let me share my screen. Okay. So as another project regarding the extreme universe and specifically gravitational waves, I set up a tutorial for other researchers and students to show how you can use EOSC to start and pinpoint an analysis of gravitational wave data. And the scientific case in a nutshell is that we've seen in the last 10 years a number of these gravitational wave events which are produced in the context of extreme events such as massive black hole mergers or neutron stars, and can also be produced by another range of astrophysical events. They are pretty important because they can provide alerts to other electromagnetic observatories, such as gamma-ray burst telescopes or optical telescopes, and they can be used to study the so-called multi-messenger events, which produce both gravitational wave, neutrino, and electromagnetic data. So in the context of first escape and later on now EOSC Future, we started developing in collaboration with Trust IT Services this real-time analysis pipeline for multi-messenger astronomy, which is called WaveFire. And I will show here our sub-module of WaveFire named the Wavelet Detection Filter can be used to start an analysis starting from EOSC. And the starting place in this example is the EOSC marketplace. So we started from an agnostic point of view, and we wanted to see how a generic user could browse the marketplace resources, and we looked for some gravitational wave data with simple queries. We found this interesting resource, which is the Gravitational Wave Open Science Center Event Portal Snapshots, which are a collection of JSON files which contain data characterizing events produced during the different science runs, which can be gravitational wave events, for instance. And we used these snapshots to download the data, and using a custom branch of the WDF Python library for this EOSC test case, we loaded the data locally and added it to this repo. What we did then is trying to use the EGI notebooks through the academic check-in and obtaining very fastly and rapidly the specific virtual organization to use these notebooks. And we also tried to use the binder, which basically allows us directly to give the GitLab repo and its branch to reproduce the environment and the notebook in real time. And this is, I think, a great resource even for reproducibility of our test case. A number of parameters regarding a specific event, and in particular, we use start parameter to find the data and the gravitational wave open science center. I show here an example of how this data looks like in the Jupyter notebook, and it's a simple gravitational wave time series, which is the sum of the interferometer noise, such as LIGO or Virgo, and hidden there is a signal which is at the moment not observable in this data, since it has a very small amplitude. Running the analysis is very simple. It's actually a configuration file which I haven't shown, and a couple of lines of which you can see here in above the pink tab. And basically, the result of this is producing a number of events, an event list so-called, with associated quantities such as the GPS times, the duration of the event, the energy of the event, the frequencies, and storing them into this CSV file. Furtherly, we used these triggers produced to reconstruct the gravitational wave signal near the expected GPS time. And you can see here on the right the time series of the chirp signal, and on the left the corresponding chirp in the time frequency domain. So this is a simple analysis, but was done very fastly, and starting just from EOSC and without any knowledge of gravitational waves, basically. And in a nutshell, so what we did was to use the EOSC marketplace, first of all, to find resource indexed, and in this case, they were indexed through Zenodo. We downloaded these resources to find GPS times of astrophysical events, and then we did a number of tests. We tried to access EGI computing resources, and we tested the notebooks in order to reproduce the analysis. We then downloaded the open source data from the publicly available Gravitational Wave Open Science Center, and we carried out this simple gravitational wave analysis using our specific custom wavelet detection filter library, which is planned to be soon uploaded on Zenodo, and therefore be visible to the marketplace. The added value by EOSC in this particular test case was the availability of finding a large number of data sets regarding our scientific test case. There is a very large number of resources indexed, for instance, through Zenodo into the marketplace. Then we used the computing resources of EGI, and specifically the notebooks, to reproduce the analysis. And this can be specifically connected to the reproducibility of the analysis starting from the GitLab repo, which is particularly suited for student training. So this is my use case story.
Thank you very much. Before we move on to the next presentation, I actually just wanted to put a quick question for Hilde, Alberto, and Danny. You all touched on, of course, the added value of EOSC, but maybe you could speak a bit more on, not just the importance of how to make data available, but the education component, whether it's researchers or students, and eventually the general public. So if any of you three have any insights on the education component of EOSC Future and using EOSC as a tool to help educate not only how to use EOSC, but also how to do research, that would be really interesting.
Well, I can start, I suppose. Well, so the fact that we can both search for new data through EOSC and access computing, and as well to publish our results, makes it a good platform, I think, to both share our work within our collaboration, so people can reproduce our results as part of our team without having to have all the compute available to them on site. And also the fact that you can just share your recipes in a way like Jupyter notebooks or whatever, means that anyone that just reach back what you've put out of like on on Zenodo, for example, can just bring your data in, bring the code in, and then just run everything out of the box in a way. So I think that is a good platform to, well, for education, for example, so that people don't have to start everything from scratch every time. And for students, it's similar, I think, like not every student has access to a large amount of compute. Not everyone has a large laptop with a lot of storage, even though you're not like a, yeah. And so therefore, like, for example, like our bachelor student, when we first started to work with them, their storage space was pretty limited and so on. And so having access to remote compute and remote storage meant that they could just, within an afternoon get started with the project and reproduce our results and continue on with what their research project was about. And so in that sense, it was a good platform for that as well. And then therefore, like also once you start working with these platforms, you also get within the community of EOSC Future, and then they quickly got in touch with people at CERN, and that also got them quite excited, I think. And so yeah, there's plus value not just in the tools and services, but also in the people behind the whole platform, I think. So that would be my pinch of salt.
Thank you. Does anyone else want to weigh in?
Yes, I do agree with Dani on the point made, and specifically for student training, I think the availability of reproducing basically pipeline, for instance, which can be gravitational wave pipeline, or a simple analysis right out of the box by simply loading, for instance, a GitLab repo which shows tutorial and having available a notebook directly to use and analyze. I think it's extremely educative, and also this can be done especially for even early career resources in a collaboration to show results and allow them to reproduce the same results in a fast and easy way. And I do agree. So that's my experience, at least.
Thanks. Hilda, if you don't want to add anything, we can move on to the next presentation, but feel free to speak as well. I think we'll go on to the next presentation. So now we'll move to another project. Dr. Martin Sudmans, who's a researcher at the Department of Geoinformatics at Paris-Ladron University, Salzburg in Austria, will speak about a semantic Earth observation data cube infrastructures.
Thank you very much. Hello, everyone. Good morning. I hope you can see my screen very well. So I present a topic that we are working on with the support of a C-Scale project. It's about semantic Earth observation data cube infrastructures. I explain quickly what this is and why we think this is important to have. Oops. So I guess not everyone is familiar with Earth observation, but this is the short overview of the situation we are currently facing, or we are facing in Earth observation in total. So I appreciate and very enjoyed the previous presentation about the space. Let's say now we're looking from space down to the Earth again. What we see on the top left image is a satellite image from an optical instrument acquired by the European Sentinel-2 mission of Salzburg. And I would say this is a very favorable image because you see there is no cloud, there's very few topographic shadow or any kind of disturbances. But this is very rare, in particular in Austria. We face other situations as well, which you see at the bottom. We have a lot of clouds, unfortunately, which is noise, but you can also analyze that, but we usually consider this as noise because we cannot look through the clouds. We don't know what is below the clouds. There are sensors which allow us to do that, but not optical ones. On what you see on the bottom images as well is, in particular in winter, the situation is a bit difficult because we have long shadows from the mountains. they're difficult to analyze. Also, in particular, this situation, and you see that with the snow, is a very important one to analyze in the context of the climate change. So we have the situation that the data is not easy to analyze, and the second problem is that it's quite large. We are talking about approximately 8 million images acquired every year by the Sentinel-2 mission alone. That means we have for every part of the world at least one image every 5 days. And the higher you go to the poles, the more often, obviously. So in Austria, it's about 3.5 days. This gives us a lot of opportunity to analyze with a very dense time series. We can track the changes on the Earth very densely. But given the constraints about the data size and the problems, the contamination, it's not an easy task to do. And this is exactly what we try to tackle with our semantic data cubes. The previous, let's say, workflow, which you see on the left side, is that you as a observation analyst, you download the data somewhere. There may be even only one image. You do your processing on your computer, and then you create a map and you deliver it to the user of the map. But in this new situation, this shift that it needs to shift. So the data provider puts the data in the cloud in a format that is so-called analysis ready. The analyst logs into the cloud to do processing there. And instead of, well, then there are two options. You can either download the results and then send the results to the map user, or you send the link to the result to the map user. But the main issue here is you want to limit the movements of the data and process everything in the cloud. One of the main drivers for this approach is the so-called data cube, which allows to analyze or store and manage and analyze the data in a spatio-temporal way. In our approach, what we do is we have a semantic enrichment processing pipeline attached to it. So every image that's in our data cube is automatically pre-processed, and the difficult to analyze spectral signatures of vegetation, snow, cloud, and so on that you've seen was in the first images was a bit different for all of the images. They all get a category. So every pixel knows what it contains. We store all of this in the data cube that allows the scalable analysis through space and time, and provide a user interface with a semantic querying based on these spectral categories. We'll show an example how that works. But first, about the semantic enrichment. So you have to consider this is like a semantic skin on the Earth. You have the data, but on top of that, you have the spectral categories, which is not yet land cover, but it tells you whether it is vegetation or it is water or it is snow. You see that in the bright blue. And as a user, you don't have to create complicated algorithms. You can directly use these categories for your analysis to see, for example, whether the snow is changing or vegetation is changing and so on. This works for every image on the world. It's completely and fully automated, and it is very scalable. This is an example what you can expect from that. On the bottom left, you see the legend. You don't get the information whether there are cars or whether this is a city center or these type of semantic information, but you get the information whether this is vegetation or bare soil or water and so on. This is again Sentinel-2 example from the border between Salzburg and Germany, with the original 3 of the 13 bands, which now looks like this. And after it goes through our processing chain, it looks like this. So each of the pixels now gets a category that can be used. What you see, for example, consider the different colors of all these lakes. And once they gone through the processing, they all get the same label water. And you can simply select label water and you get all of these pixels. This is the main idea behind the semantic enrichment. Now in the data cube, we store all of this in a spatio-temporal oriented way. So the pixels know where they are located in space and time. And you as a user, you don't have to deal with files and open files and need to know about the internal structure of the data center and so on. What is exposed as a query interface where you can directly input the real world coordinates. So you have the information that your area of interest is in a certain location of the world. You have the coordinates for that. You are interested in a certain time span, let's say 1 year, and you send this information to the data cube, and the data cube collects from the cloud all the information to you, for you, and then presents it to you in a way that can be directly analyzed. Also on the top, in the bottom right, you see an example in Python how that may work. And behind that, there could be petabytes of data, and it's just a few lines of code, and you're ready for analysis. In our approach, we extended a bit because we saw that a lot of users who may be scientists from different domains, but also from general public and public authorities and so on. They are not very familiar with programming. Some of them are, but a lot of them are not. So we created also a graphical querying interface that can be used directly from a web browser. So there's no need to install a software on your local computer. You can use that graphical user interface. And how that works is you create these semantic models where you specify the process that should be applied in the data cube in this drag and drop workflow builder, let's say, with the semantic categories. And it will then be applied to the data cube in spatio-temporal dimensions again. This is then stored as a so-called semantic model in the knowledge base, and you can share it with other users, and you can reuse it, and you can trigger the processing from various clients. This means someone creates a semantic model that does an analysis of Earth observation data. Someone who is an expert in the specific topic gives it to me. I can execute it and get my result directly in the cloud. Now, since we have this dense data cube with every 3.5 days a new image, we can create, answer several questions. For example, here, how green is Austria? This is a map that shows the percentage of vegetation in a certain time frame. And you directly see where green vegetation is, and you can track this over time. This is a very important information because vegetation loss is bad in many cases, for example, through soil sealing, construction processes, and so on. A big problem in Austria, which needs to be tracked very closely. But also vegetation gain can also indicate negative processes, for example, when glaciers retreat and then the vegetation increases in high altitudes, which is an indicator of and the response from climate change, for example. So this needs to be monitored very, very closely, and with these tools you can do that. On the other hand, what you can also do is, since we have this dense time series, you can go to a specific location and trigger the processing there for detecting a time series. And in this case, you can monitor the construction of the building. And you see in the time series, the green curve, for example, is a large vegetation or strong vegetation, intense vegetation, and it certainly dropped, and it drops forever. And you see the environmental impact of construction, for example. Currently, we have that data cube for Austria, and with the resources we have, we do analysis very successfully on this data cube. But the target is to the target is to create these data cubes for every part of the world based on user request. Our infrastructure or architecture allows to operate concurrently multiple semantic data cubes. And the idea is that you can select an area where you're interested in, instantiate a new data cube, and then trigger your processing there, and you get the information from that part of the world that you need. So this is what we are heading. What is a requirement is that we have enough resources to do the semantic enrichment. Also, it is quite lightweight, but still, given the amount of data we have and the amount of images, this is computationally quite intensive. That needs to be covered. And what is also necessary is that the data, and in particular high quality data, is available and ready directly in the cloud, and I can connect with my tools there. And this was all from my talk. I'm happy to answer questions.
Thank you very much, Martin. I don't see any questions in the chat, but if anyone would like to raise their hand, quickly ask a question. Otherwise, we can go on to Tatiana's presentation and then so we can do the two more presentations before we go on break. Maybe that would make the most sense. But if anyone has a question now, feel free to raise your hand.
Good morning.
Hi, Charisse. Yes.
Can I have a quick question?
Yes, please.
Yeah, Martin, thank you very much for the presentation. We know each other, so I do know what you do more or less. I was now thinking as you were talking, what kind of stakeholders more or less use these semantic data cubes? Like, do you have people from the public entities like ministries, etc., that use it, or can you give us an idea?
Yes, thank you. That's a very important question, because in the end, someone needs to use the data and make use of the data. And this is not easy and a difficult task for various reasons. But the information we generate from our data cube is used by several authorities in Austria for agriculture, also the environmental agency and the regional planning, for example, in Salzburg and other countries are using that. We are not there yet at the moment where they do the processing on their own. But what happens is that we do the processing and deliver the data, or we do the processing together with them. So this is eventually the idea is that everyone who is interested can do the processing on their own, get the result, and embed it in their workflow. But this is a long process.
Okay. Yeah, as you mentioned, not many of them are familiar with programming, like advanced programming and stuff like that. Yeah. Okay. Thank you very much.
Thank you.
Okay, thanks for your question. We'll go on. So now Tatiana Stim from Kappa Zeta Limited in Estonia. She's a machine learning engineer. We'll hear a bit more about use cases using cloud and cloud segmentation.
Yeah, hi, can you hear me? Yes? Okay, I will share my screen.
Your presentation.
Yeah. Okay, so today we'll talk about our use case, which is providing Kappa mask-based cloud-and-cloud segmentation masks for every Sentinel-2 product over Europe. So first I will talk about what Kappa mask is, and then I will go more into details of the implementation of the use case. So let's start. Well, everyone who worked with the optical satellite imagery knows that clouds sometimes can be a pain. So that's what we know too. And lucky for that guy on the side that he knows what Kappa mask is, and now you will learn too. So Kappa mask, we created it, we started working on it in 2021 with European Space Agency. And then it was the project about creating cloud and cloud shadow segmentation, a cloud masking processor for Northern Europe. And then in 2022, we switched to the global conditions and worked on that. But the idea that Kappa mask, it takes Sentinel-2 product, both level 1C and level 2A, then it splits it into subtiles. Then we run DeepLab-v3, which is a semantic segmentation model on each subtile, get predictions, merge them together, and we get the final mask for the entire product. Yes. So we also created our data set, again, cloud and cloud shadow data set. So it has name Kappa set, and I will and a shared link later. And it has around 10,000 subtiles of the size of 512 by 512 by 13, because it was for level and 1C. And then more about results, because yeah, I thought that guy on the slide was very happy to use Kappa mask, but why? So here you could see a comparison on the same image that you saw before of the Kappa mask and other cloud masking processors. So here we have two machine-based cloud masking processors, which is Kappa mask and S2 Cloudless, and there are other rule-based. Yes, so Santokorov, Maski, Depix, and Maya. And you can see the labeled, which were labeled per our labelers, and the prediction is here. And you can see that, for example, F-mask really thinks that there is some cloudy thing happening on the water. Then there is some misclassification in Centaur with shadows, as well as some with EDPX here. And then, yeah, S2 Cloudless doesn't have shadow and semi-transparent class at all. So it has detected clouds only. Yes, and then we also, for us, it was important for cloud masking processor to be fast. And then we compared how fast Kappa mask in comparison to Centaur mask at the business to Cloudless. And you can see that when you run Kappa mask on GPU, it's almost 2 times faster than Centaur and F mask. So it's pretty good time, and most of the time actually goes to the subtiling process and then the prediction. Yeah. So then we thought, we think the Kappa mask is pretty nice, and we know how important it is for researchers or other companies to have good cloud mask. And we thought that, maybe it would be great to compute Kappa masks for the entire Europe and host them to make them accessible to everyone who is interested in it. Yeah, and then we found the C-Scale project, which was a wonderful opportunity to do what we wanted to do, which is, prepare Kappa mask and make them available for the world. And now I will talk a bit more about how it was set up. So at CreoDS, it was set up with the help of Python RQ. So the idea that is there is a fetch worker that looks for new products which we need to process, and then it gives passes this product to other workers, which is subtiling products. This is CMVSM. We have two of those, but they work in parallel. And then the sort of output of that worker goes to the CAN-Predict, which is already the prediction process itself. It's where it runs the model on the subtiles as well as merging them together. And then post-processing, what it does is just basically removes all the temporary files that were created during the run, because CMVSM, for example, which is a splitting tool, here it creates, so it splits into the subtiles. So we have 484 subtiles, which is netcdf files. And while doing that, I think he creates around like 5 gigabytes of temporary files, which is a lot. So we had to remove those. And then also when CAN-Predict, the predictor, we run on subtiles. It also creates, in addition, some temporary files. So those, all of those are removed in post-processing. And the Python
Okay, it seems like we lost Tatiana.
now.
Yes.
Yeah, so 1 minute ago, was I still here? If I was there, I was talking about...
Yes, you were here. You were talking about it, yes. Yeah.
Yes.
Okay, thank you. And then, here I was talking about the OpenStack, that we got a dedicated project environment there. And it wasn't me who set up everything, but the person who did it, he said it was wonderful, such an easy experience, because setting up virtual machines was very straightforward, as well as volumes setting up was very straightforward. He really liked that it was very easy and comfortable to access the Sentinel data because of those predefined networks, meaning that all virtual machines have all the networks mounted by default. And he said that the only thing that took time, it was figuring out that the default Ubuntu user is EO user and not Ubuntu. So that's what he said. And then our current results, so you can see the distribution of the Sentinel-2 products. Doesn't look like the entire Europe, but I think we were very ambitious in the beginning, because initially we planned to calculate so all Sentinel, all kappa mask, calculate all the kappa masks for Sentinel-2 products for over entire Europe from 2015 to 2022. So it was a lot. Currently, we are at this state, so we have 30,389 calculated. It was yesterday, so today it's around 31. And we started processing in January, so some months already passed, 4 months passed, and and the entire it takes 52 gigabytes to store the kappa masks for those products. And also initially we calculated a kappa mask for all the products from the time range between January till December, but then we switched to between March and October, because those kappa masks, at least from our experience, are like a bit more important, because if you want to do some crop detection, damage area detection, those months are usually more important. And autumn in Estonia is very cloudy, for example, so doesn't really help the data. And then, yes, so to conclusions, it was very wonderful experience. I know that I heard that setting up the entire pipeline was really interesting, as well as they using OpenStack project with that easy access to the Sentinel data. It was a wonderful experience, as well as we could use multiple computing resources, which was flexible. We could add as many subtiling workers more as we need them. And currently, I know that KZ has discussions with testnet about storing the final products. So then they finally will be available for researchers and everyone who needs them. We really hope it will help someone to some extent. So yes, and if you have more questions, you can always write to me. I can help with Kappa Mask if you're interested in that. Or if I don't know anything, something, which probably don't, I will ask my team to help. And thank you very much. Do you have any questions?
Thank you.
Okay.
Yes, no. I think let's go forward with just one more presentation, and we will do a kind of recap, ask maybe one or two questions before the break. But thank you very much for your presentation.
Thank you.
So now we move on to another area of applied science, and this is biomedicine and the use of computational tools. And we're going to hear from Dr. Nargiz Zarabi, a senior advisor at SURF in the Netherlands.
Hi, good morning. Do you hear me?
I hear you. Yes.
Share my screen. Do you see my screen?
Yes.
Perfect. So good morning, everyone. My name is Nargiz Zarabi, and well, thank you for giving the opportunity to present the work we have been doing to use DICE and EOS data management services in the computational biomedicine community, which is a community which does a lot of research, has been doing a lot of research in the past years, data-intensive research, also compute-intensive research, and has had a real need for proper data management within the community. So I'm not going to present the actual research work, but how we try to work with the research with the community to help them better manage their data, of course, using the DICE and EOS services. So a short introduction. I'm from SURF. SURF is a collaborative organization in the Netherlands for supporting research and education in IT. And we host big infrastructure, the supercomputer, cloud services, but also data services for online data, but also data that need to be preserved for longer term. And we are also involved in various projects, European-wide, national-wide, but also European-wide, like as you see the DICE and EOSC projects, EOSC Future, and also community, more research projects like, for example, Biomed, which is standing for computational biomedicine. And we don't only provide infrastructure, but we also give consultancy, trainings, and do knowledge exchange with our partners and also researchers. Computational biomedicine, it was a European Commission Horizon 2020 funded project, and it's one of the Center of Excellences that focuses on the use and development of computational applications in the biomedical field. It's a big community with lots of partners and various user groups in different fields, from academia to industrial users, clinical users, and also the general public, which is, well, in general interested in this area. the community is moving toward exascale for compute. As I said, it's a very compute-intensive field of research with building all types of simulations from human heart, blood flow, all the way to virtual human. So very interesting research is being done. As I said, I'm not involved in the research myself, but what I've been doing is try to see what are the challenges that the researchers in this community face and how we can help them to improve on the way they handle data. So as you see, the main challenges that researchers face, it's a European project, so many different partners all around Europe are involved, but also collaborations with the universities or researchers in the US or other parts of the world. So there is a big demand for efficient data access and data sharing and data transfer, especially intensive data sharing and transfer, and also restricted data. Also preserving research data when the research is finished, when the how do they make backups of the data, archive the data, make sure that the data is preserved over longer term, and also data provenance, making sure that the data is accessible to all the researchers within the community, but also other communities by means of using persistent identifiers, publish data with domain-specific metadata, and all types of things to do to make sure data is findable, which is one of the major challenges within scientific communities, to discover data, because I think being able to reuse data is as important as of being able to generate new data. So I think these are challenges that is not specific for this community, but in general for all research communities. And within CombioMed community, one of the main challenges was, first of all, lack of an encompassing solution for publishing data and metadata, and making sure that the data is findable. You can think of, for example, metadata schemas, that if researcher from this community wants to publish the data, they need to be able to publish it in a repository which has the metadata fields they want to publish. And also the technical knowledge and awareness in general about these FAIR principles, which is becoming more and more important within research fields and data management, to make sure that the data is findable, is accessible, interoperable, and most importantly, reusable by other researchers and other research communities. So these are I think, things that has been historically not very well taken up, and we tried with this work to make sure that, well, this community also keeps up with these important data management principles. Just as an example of a research use case within CombioMed, here you see in silico human clinical trials for cardiac safety assessment of drugs, which is using an application called ALIA application. And this is an application that is being run on the supercomputers to make simulations of heart, and make meshes and all kind of different slicing and methods to make a simulation of a heart, and also to assess how and why do drugs may produce certain effects, or help the doctors to assess these behaviors. As I said, ALIA is an application or a simulation code for high performance computational mechanics, and it solves very complicated coupled multiphysics problems. So you can imagine that when these applications are being run, also lots of data is being fed it into the application as an input, and also it generates a huge amount of output data, which also need to be analyzed. And researchers are have been using these applications in several HPC centers within the community. But again, when it comes to collaborating between partners, like, for example, this application was developed in Barcelona Supercomputing Center, and this is, well, the slide is made by one of the researchers at Barcelona Supercomputing Center. When it comes to collaboration between, for example, Barcelona Supercomputing Center and UCL in the UK or SURF in the Netherlands, then the researchers face the challenge of large data sharing, intensive data sharing, etc. So the workflow that in this particular case the researchers were facing using the ALIA application was that the data was created in a lab in France, and the data was stored there, but also a copy of it was shifted to the Barcelona Supercomputing Center, because high performance computing was needed to be able to process this data. And then, of course, these researchers at Barcelona Supercomputing Center could also get allocations to run HPC infrastructure at SURF or other centers. So and also they had collaborations needed to do data sharing. So this data needed to be replicated to the other sites for either analyzing the data or to make sure that replicas of data is available for long-term preservation or for giving access to other researchers. So their data replication between sites was one of the important needs. And then, of course, once the data is replicated, it can be used on for example, the Snellius supercomputer at SURF, which also has the ALIA application installed to run analysis and generate output data, which can be used for further studies. So to facilitate that, we within Combiomed, so the sort of collaboration with the DICE and EOSC and tried to use the services that has already been developed within these big European projects for data management, and also mainly the EUDAT services, and we tried to implement two workflows. First of all, the data replication workflows, which facilitates large data transfer by making replicas of data between different sites, and also making sure that the researchers can publish their data. So a sort of data publication workflows, which researchers can publish their data in a repository with metadata schema specific for Combiomed, so that they can publish community-specific data. So the partners involved from Combiomed were UCL in the UK, the Barcelona Supercomputing Center, and also SURF in the Netherlands. And we tried to put a technical solution in place, but that was not the only thing. I think two main aspects that this collaboration brought was also training and educating researchers in this whole move of data management and FAIR, and also setting up good networks to share knowledge, etc. So it has been a very valuable collaboration for Combiomed, also to use the expertise within DICE and EOSC to set this, the platform that I'm going to show you. So the EUDAT services that was used to set up this data replication platform was, we aimed to use three of the services: the B2Share, which is the data repository for publication, where you can make metadata schemas per community. Combiomed is already added as a community in the B2Share. Then the B2Handle service for making persistent identifiers. As I said, one of the big needs within the community is to make this data findable. So B2Handle service was used to make PIDs for the data. And the B2Safe service, which is based on iRots and for staging data, replicating data between different sites, which have the B2Safe node deployed, and also, well, bringing data close to compute. At some of the sites, like at SURF, our B2Safe instance is connected to tape storage in the backend, and so it also implies that the data that is within the B2Safe will also land in tape for long-term preservation. So this is, well, the data platform that I talked about. As you see, we had 3 partners involved: UCL, BSC, and SURF. And so within the BSC, a B2Safe node is deployed, and it's been federated with the B2Safe endpoint at SURF. At SURF, we are running B2Safe as a service in production, so we have been sort of also leading this, helping these other centers to set up the B2Safe. At UCL, B2Safe was set up from scratch, which was deployed as a service. It's still in a pilot phase, but we have made federation between the B2Safe at SURF and UCL. So what you see here is that data that is being generated at UCL or in the UK can be replicated at SURF, and then also with an iROS tool, it can be replicated to BSC. So making replicas of data is made possible. When I'm talking about data, it's usually like large amount of data, like think of terabytes of data, which is not easy for a researcher or research team to just transfer it through normal means. So that's why we set up this platform to help them out with replicating data. So federation, let's say federated network of B2Safe endpoint is more or less in place. We are now, well, missing the link still between the UCL and Barcelona Supercomputing Center, but for now we are running different test scenarios to replicate data between the 3 centers via SURF, and also doing performance tests, etc. As I said, the B2Safe endpoint at SURF is also connected to the tape data archive. And well, if data need to be preserved for longer term, 10, 20 years from now, we can ensure that that's possible. We are also using B2Share service to make data publication possible. At SURF, we do have an instance of B2Share running, which is called the SURF Data Repository. We are also have made the combined community within the B2Share central instance, and some data has been published there. So this to set up this platform, we started from making a work plan and, well, all types of technical work that has been addressed. As you see, within the BSC, as I said, we have deployed B2Safe and B2Handle, federated that with SURF instance, and, well, made sure that enough allocation storage is allocated to do the replication. We are now doing the performance test, the same at SURF and also UCL. So UCL is particularly interesting because they started to deploy this service from scratch. So if you are an institute and you think that you work with this community or with similar communities and you would like to have a B2Safe service deployed, well, I think what I'm in the next slides, what I'm going to show could be used as a good example of how this can be set up. As I said, B2Safe deployment at UCL, we did it from scratch, and it involved, well, a lot of work, I must say, but also a lot of lessons learned, which we are going to document in a so-called technical report, so that to make sure that if new institutes or organizations want to deploy the service, what are the best practices, or can benefit from the experience that we have made in this collaboration. I'm not going into the technical details of how this was deployed and made sure that it is connected to an already existing ecosystem at UCL, but just showing that it required some effort, and it's still it's in a pilot phase, and we are working to make this better. And at a certain point, the decision needs to be made if this will be offered in a production level or not. But maybe more interesting is, the difficulties and improvement points that we have faced. Usage installation information was spread all over different sites and wikis, and so we had to come up with a consistent manual to how to do this. Also, we noticed that different versions of iRoads and B2Safe and different versions of Linux machines. Certain versions should be used to be compatible, etc. So we also had a lot of lessons learned there. We were in a good contact with the B2Safe core team to get support in setting up things, but still we think that support can be there is a great demand for support in setting up this work. Also, the internal policies at the organization was a big hassle to get around with, especially the security and maintenance purposes. How we convinced the security people that this can be connected to a service that is already in production, etc. So it's as I said, we come up with a big list of lessons learned, and I hope that this can be used by future organizations which want to use these services as a base for data management. This is also a sort of future concept, how we see the platform growing, because right now we have 3 partners within Biomed involved: UCL, SURF, and BSc, but we would like to extend this to the other partners, like, for example, LRZ in Germany, and make sure that all centers or even research labs or institutes that are involved in the community can easily connect to this network. It might not need that they all need to install B2Safe, but make sure that through, for example, sync and share services, or they have a good connection to this network, and can bring the data close to the HPC center, and then data can be replicated through this platform. Again, safe data replication and preservation, allocation of PIDs to make data findable was the big things that we have achieved in this work. Also, the metadata schema for Biomed community, which we also worked with and come up with certain fields that was specific for this community, that needed to be filled out to make sure that the data can be findable. And I think, well, this brings me, one last slide. So it was, as I said, not only about bringing technical solution, putting technical solution in place, but also giving training and sharing knowledge and making awareness. And as you can see, several events has been organized to help the Biomed community keep up with this topic thanks to the DICE and EOSC efforts for this. And this brings me to my last slide. I want to thank you for listening, and also the people who I've worked with to set up this platform. And if there are any questions, I'd be happy to answer.
Hello, everyone. Welcome back. This is the second part of our use cases from the EOSC Community webinar. And now in the morning, we heard from different projects, C-Scale, EOSC Future. And now we're going to go on and we're going to hear from Anne Fouillou. And she's a senior research engineer from the Simula Research Laboratory in Norway. So feel free to take it away.
Thank you. So, let me share. So hopefully you see my screen. And so I will talk about the PanGeo community. So PanGeo is a worldwide community, and we promote open, collaborative, inclusive, and reproducible and scalable big geoscience data research. And we are very grateful we have done this work with EGI-ACE. All the members of the PanGeo community are volunteers in this project. So it was really a great opportunity, and I will explain you why. This is the agenda of my talk, and we'll have a demo at the end. I will introduce you what is PanGeo, but very shortly, and mostly to set the stage, what has been done within the PanGeo EOSC and the EGI-ACE, and how we move to a more community of practice with the environmental data science book, and I will show you with this demo. So what is PanGeo? If you are working in the environmental data science or climate science, maybe you have already used PanGeo. So PanGeo is very modular. We have everything is about integration, and we have different components. So we have a user interface, and for instance, when you use a Jupyter or Binder, and you are using as a data model XRA, you are already using PanGeo. For accessing the data, we are using standards such as Stack for spatial temporal asset catalogs to be able to access data, for instance, on remote object storage or intake. And we are trying to have data on cloud optimized analysis ready data like Zara or Parquet. And we also use NetCDF because this is very classical in climate science. So we can leverage different kinds of storage system. And what is really very important, and what was new in the EGI-ACE, is to be able to leverage a scalable compute. So for instance, with Dask, and have different types of resource management depending on where you are running. Because what is very interesting with PanGeo, the PanGeo platform can scale, so from the laptop to the cloud or the HPC. So it makes it possible to explore geoscience data. So in a very interactive manner, because we are using the Jupyter ecosystem. And it's very important because when you're a researcher, you usually prototype on your laptop. But when you want to do something larger, you have to go on larger resources, such as cloud resources or HPC. So what have we done within the EGI-ACE project? So we submitted a use case, and one of the main goals of the PanGeo community was to have on-demand PanGeo deployments on EOSC. And for this, it has been done, and this is EGI-ACE. They have done it through the infrastructure manager. So it was very simple for us as PanGeo community to be able to deploy different PanGeo ecosystem on EOSC. So we always have the EGI check-in, which is very important. So when we onboard users, they always have the same way of authenticating to a PanGeo deployment on EOSC. And we have, of course, Jupyter Lab and the Jupyter ecosystem with the XRA and all the different packages we are using for environmental data science. And we are also trying to connect with other services, for instance, RUHub, which is a Research Object Management Hub. And Elisa will show you more in details what you can do with it. And very important on the right-hand side is to be able to leverage different type of infrastructure. And what was very new for us and in EGI-ACE is to have this Dask compute aspect. So to be able to parallelize data analysis with the Dask cluster. And this is something that was really new because all the deployments with this Dask compute were only available on commercial clouds or mostly on US deployment, for instance, with 2I2C for the PanGeo community. So, because what is really very important for us is to be able to scale, and Dask is a key component for us. Before I was in the Reliance project and I was using a lot of Jupyter ecosystem and EGI binder and EGI notebook, but the thing is I could only use very small use cases or develop small use cases. Well, with EGI-ACE, now we have the possibility for one user to be able to create what we call a Dask cluster, and we can parallelize with different workers, and each worker will work on a small portion of the data. So if we have a lot of workers, we can analyze very large amount of data. And it really enables open science on real-world scientific application and not only on small use cases. But Dask is something which is usually new for researcher, and we had to learn how to use it. So if we want to be efficient on this infrastructure, we had to learn how to analyze data with Dask. So we have developed, because we can do this on-demand deployment, we have developed the concept of training infrastructure as a service. And what we do is we onboard researcher and we teach them how to use the PanGeo ecosystem on EOSC, but we also, more importantly, explain them how they can parallelize their work with Dask. And we have run different events. So for each event, we can make a new deployment. So we have made a small workshop on the Force4G, which is an open source software for GIS. In 2022. So it was a short workshop, like a few hours. Then we did a longer Clever bootcamp in 2022 at the end of the year. And this time it was for researchers. So it was really for real work. And they came with their own use cases, with their own data, and they analyze and they learned to analyze first using the infrastructure, and then they did their own research work during a month. And we also run another event, which is the e-science, and this one for master students. So here was more to teach them how to analyze data with Python and XRA, and also a bit of Dask. Overall, we have onboarded 100 researchers, more than 100 researchers on the EOS platform, and we have used more than 4 million CPU hours. So if you want to know more, we have they have done a very nice summary of this work. And then when we were doing all this training and when we started to work with researchers, we realized that if we really want to work open science is not only about infrastructure, it's not only about training. So we train how to use the infrastructure, but we also need to learn and to agree on how we work to make open science. And if we think about only the Jupyter notebook, for instance, at the beginning, you can have an idea on how to make your scientific work. But if you do it on your own, it's most likely the quality will not be very high. Well, if you start to collaborate, you can work with maybe someone is better at improving the narrative, someone is very good at making a nice visualization, and some other people can review, etc. And this way, we can really do open science, but we can also have much higher quality Jupyter notebook. So this is what we call this community of practice. So this is really here to ease collaboration and get high quality community driven and reusable notebook. And what I mean by reusable notebook, I will explain you. This is really to make it reusable, and you can select some part of the data analysis and make your own analysis. So we do it in the framework of the environmental data science book, and I will show you in the demo. And one of the mission is to educate and leverage good scientific software and data management practices among environmental scientists through peer-reviewed, findable, accessible, interviewable, and reusable executable notebook. So the vision, I mean, this is like at a long-term vision, is really to enable environmental scientists to work collaboratively and to demonstrate and communicate their science through fair executable notebook. So this initiative is led by Alejandro Coca-Castro and is working at the Alan Turing Institute. So they are really used to onboard and have community-driven events. So let me show you what is the environmental data science book. So the goal is, again, like the Pangeo, is to promote reproducible, scalable, and shareable environmental data science through executable notebook. And here you see a bit the process, which is divided in 3 phases, where you have the contribution phase, which is collaborative. So we really want to work in the open, and this is why we leverage the EOSC notebook, EGI notebook, and with a task cluster behind to be able to do large data analysis. Then we have a collaborative review process, and I will show you this is fully open. And here, this is really to improve the narrative, improve the technical aspect of the Jupyter notebook. And then at the end, we'll publish. And when we publish, we will get we will give Zenodo a digital object identifier with Zenodo. And for this, we are using a research object. So this is what the gallery looks like. I will show you in real. And very important, we try to have a process where we give guidance on how to write a proper Jupyter notebook to be reusable. Because reusable or reproducible is not I click on the button and it will execute and give exactly the same results. What we want is to be able to read as human and be able to reuse the content of the Jupyter notebook. So we provide some templates. So very quick overview of the open infrastructure for publishing. So at the beginning, you have an idea on how to write a scientific Jupyter notebook, and we provide different templates. So the templates already have the different section, and we have template for working in Python, in Julia and R. And then we also leverage the EGI binder or the EGI notebooks. And then we are using RoHub, so Research Object Hub, to be able to have a persistent identifier as soon as we have created the Jupyter notebook. And this will make our work more findable and accessible from, for instance, from the EOSC Explorer. And to make sure we are reproducible, all the computational environment and everything is containerized. And we put the image and query. And very important here, which is also what I will show you, we have an open review process. Once the review is finalized, we can make a snapshot and get a digital object identifier in Zenodo. And then later on, when the Jupyter notebook is published, we can also have another iteration. If someone, when reading the Jupyter notebook, would like to improve it, we have this post-publication, and they can become contributor, and we'll make another snapshot and get another digital object identifier. And everything is rendered with a Jupyter book, so you can read the contents. And I will show you what it looks like in this demo. And we'll start from this environmental data science book. So this is how it looks like. And very important, we have some information on how to contribute. So here we have really precise guidelines on how to contribute and the different roles, if you are a maintainer, contributor, reviewer, reader, and users. And we also have some guidelines, and the guidelines are customized for author, for reviewers, editors, editor-in-chief, and the community. And this really helps us to streamline the process on having very high quality Jupyter Notebook. If I click on the gallery here, this is all the Jupyter Notebook that have been published. And for instance, I can take one Jupyter Notebook here. If I click on this one, you see many of the badges here. Here, this is a research object in RoHub. It has a digital object identifier, and you see the structure. We always have the typical structure where you have the data download and data analysis and then visualization. So this is a very complex Jupyter Notebook here. It's for deep learning and CI's forecasting. But I can show you, for instance, at the end, what we want also is to have more interactive visualization. So we have some visualization, and as a reader, you can really explore what the researcher has done. So it's fully interactive. And at the end, we have how to cite this Jupyter Notebook, which is a digital object identifier here. But it also has in RoHub, go back, sorry. At the top, you have a research object. So we also benefit from the work done in the Reliance project. Let's take, for instance, this other Jupyter Notebook, same structure. We also have a research object, and it's also interactive here. And what I want to show you is this other badge here, which is a review. So here we see when it render passing, it means it has been executed and successfully. It means this is reproducible. And here we can see the review process, which is fully open, and it is saved in GitHub. And it also has some guidance on how to review. So we are providing. We need to accept the code of conduct. We have the general checks. This is for the reviewer, the reproducibility, the pedagogy, and the ethical and other requirements. And then all the review will be, you can visualize it in Review NB, which is another service, and it takes a bit of time. So I will open it here. And the main advantage is here you can see all the changes, and you can also have all the narrative, all the discussion that has been, all the different points that have been discussed by the different reviewers. So here we can see there were a lot of discussion, and it's both technical, so to improve the quality of the Jupyter Notebook from a software practices point of view, but also from the narrative. So we also have some scientific review. It's very light, but it's quite effective. So here you have all the process, and all the review is stored in this GitHub pull request. So it's always accessible at any time. And I think that's all I wanted to show in this demo. And I can maybe go back here and just wanted to say thank you. And one thing is, once we have now this environmental data science book with very high quality Jupyter Notebook, what we want is to onboard more researcher, and we want to have more high quality Jupyter Notebook. So we are working with EGI on this reproducibility challenge. And if you scan this code, I can also maybe show it here. We are running it over the month of May, and we have created different teams. So we have 7 teams, and people didn't know each other before, and they are working together, and they are trying to reproduce papers, scientific papers. So we have 7 teams working on 7 papers from the Environmental Data Science Journal. And the winner will have £500 from the Cambridge University Press, which we are working and collaborating together. And that's it for me. I will stop my sharing. And if you have any questions, I would be happy to take them.
Thank you, Anne. I think we'll continue with the presentations as we've done, but we will leave more time for more questions later. Now we're going to move on to 2 more use cases that are using OpenAIRE services for data management and cross-disciplinary research. So to begin, I'll introduce Sebastian Dahl from the University of Ljubljana, the biotechnical faculty.
Yeah, thanks for the introduction. Let me start the screen share and then, all right. Yeah, so thank you very much for the opportunity to speak today about my use case using Argus for the data management plan in my Marie Curie fellowship. So as you said, I'm Sebastian Dahle. I'm currently an assistant professor and a postdoctoral researcher, so research associate at the biotechnical faculty of University of Ljubljana. I'm also involved with EOSC as a part of one task force, a task force for the research careers recognition and credit. I'm also participating on similar topics then through EuroDoc, the European Council of Doctoral Candidates and Junior Researchers, where I'm currently vice president, and also through other organizations. But today I'm gonna show you the specific case, how I make this, how I use the platform really for my research, and so to go through. As a quick overview, we're gonna have today 3 topics, more or less, or 3 sections that I'm gonna talk about. First of all, the background. What was the reason for me to search and then use Argus? Why Argus, and how did it look like? Really, what's the solution, and how does this look like putting this into practice? And then to wrap up a little bit about the impact, how this or what this meant for me in the project. So for the scenario, this was a part for me of a research project of a Marie Curie fellowship. This project actually began in 2018 and finished in 2020. So it's already well a few years, the plan that you're going to see. And so you should also take some things with a sort of grain, but we'll take a current look, how it's looking now, how it's working, so you get a good impression. Yes, so the project, essentially, just to give you a little bit of background information, which might be important, and when we look into the planning. So this was some research project using plasma technology. The point is that it started with building of some equipment, further development of existing technology, but with building of some additional devices, putting this into practice, and then actually conducting material science, preparing samples, preparing specimen, testing them, and getting those kind of data and interpreting that. And so this was, of course, stacked as the work program to start first with the equipment to get that ready, and then go into measurements of more and more, or experiments of more and more complexity and intensity. But of course, these all do relate to each other. Now the use case I'm going to talk about is, of course, with Argus, so with the data management plans. And first and foremost, this, of course, was a requirement that I needed to fulfill during my Marie Curie fellowship. So within the first 6 months, I mandatorily had to upload the data management plan, which is something that was not really the standard practice in the host lab. And among the peers here, directly within the lab there, or within the department, there were no really previous experiences to using that. And so I went out to discover available services, how to do this, how to implement the data management plan, and how to make this useful for me, not just as a exercise that I need to do, but also as something that will serve me well. And as you will see, I think it's really, for me, something quite meaningful. It's something that I feel is not just an obligation in this case, but it's a really good opportunity to review the own practices and see where am I working efficiently, and where is maybe something missing, where maybe also do I need additional support services, software or platforms or other kinds of things. Where do I still need things to really be able to handle my data as well as possible to make the project effective, to save time and to make it work out. There were, by the time, of course, some instructions, particularly by the European Commission. They issued one Word template, which I must say was all right, but maybe not overly intuitive. And so I was looking out for different resources. First started with a different platform, but then got the got the input to check out Argos as a newly developing platform by the time. And then I actually migrated over and used Argos for the data management planning throughout the rest of my project. So how does it look like? Well, if we look into the whole data management cycle from planning, discovering, processing data, collecting data, processing data, publishing, archiving, and then later accessing. So within this large cycle of all the different services, Argos is, of course, quite at the very beginning with the planning, how do I go about it? But it's something that's going to repeat. So also throughout my project, I didn't just create the data management plan once, submitted it and was done with it, but actually I went back later twice, I think, if I remember back right, to revise the plan, because some things, how I was thinking at the beginning to go about it, this did not hold true to be really the most effective way. And so I ended up changing a little bit. And so also the status that you're going to see in a minute, this is a data management plan towards the end of the project. So project began in 2018. This is a status of spring 2020. So that really some things have changed along the way. Other services you'll also see that I have used are, of course, Zenodo. A lot of other things were either not available by the time or did not seem to make sense to me to use, but rather focus on other kinds of tools. So let's talk about Argos. Argos is, of course, there for the planning the data management. So it's something you can start with, but as I already said, it's more useful to me than just that. So it's not just a way to support open science. It's not just that it's a mandatory requirement, but research funders, it's all that. But for me, it was a very useful tool to see how to really make things effective for me, how to do these automations, and also to revise my own practices in a way to be to handle data properly. So it's something that I did as a whole process enjoy. Although I must admit, I didn't repeat this for every single project since then. So the mandatory part for me is helpful because we all prioritize our time, right? And so having this sort of nudge to do the proper way is something I experienced also as quite helpful. You can find the tool, of course, on the OpenAIRE website, so argos.openaire.eu, and it's a very straightforward tool, as we'll see. There's a lot of good services that are included into this platform, into the Argos tool, from machine actionable templates for a lot of different funders and whatnot, to an integration, for example, with the Utopia University Network portal, and many other things. But so let's directly head over and take a look how this actually looks like. So if you type in Argos, you're going to end up on the landing page, and of course you want to sign in or either create an account or log in. So let's just sign in via ORCID. For those of you who don't yet have an ORCID account, these ID numbers, it's a really nice platform. It's a really helpful tool for a lot of different services. It becomes super easy and quick to access. So as you see, it's like a one-click login process. Now, of course, taking a little bit of time because of the parallel webinar going on. So that's due to our local internet speeds. But the point is, even if you don't use it as a database for your publications and to showcase this, it's a very nice tool also to really get access to a lot of platforms and simplify things. So it's just along the way my recommendation for the ORCID. Oh, it's really taking unusually long. Let's repeat this this quickly and see. Sign in. Yes, please. All right. So here we are. My original data management plan for the project that has ended in 2020 already is of course finished, finalized, published, and all. But I created just a copy of the data management plan so we can take a look together how this looks like in practice. If you start with a new data management plan, the platform will offer you a whole wizard that will lead you through the process and really get you started very intuitively. I will skip this for the sake of the time that we have today, and we'll just directly go into the existing plan. So you see, this is the front page of the data management plan. And you also see that all the data that I was handling within the project, I compressed into a single data set description. If this is a wise decision or not is maybe up to someone else to decide. But the reason I opted to just have like one single kind of a data set that I was described and not having multiple different ones was, number one, because I had started in the Word template and then on a different platform. And so I had already building blocks available in a, for me, useful way, and didn't want to invest too much time to completely restructure this. But on the other hand, also, as we saw that the work plan that's building one work package on top of each other, still all the publications are, of course, linked to the experimental results, and all the publications did then indeed include all kinds of data, from the construction data to the most advanced analysis technique. So having all together in a single data set that will then make up, and did indeed make up the data set for each of the publications, seemed to make sense for me to have these compressed together into one block. Okay, so this already introduces a little bit of the structure. So of course there's a general introductory part with a title, a brief description. So the description, this is just copy paste of the project description. The researchers taking part, who's all involved with the organizations and so forth. And if we go forward, since this is all included, there's a lot of points that you can include. So this is a European funded project with a grant that you can very simply find by simply just putting in either the grant number or the title, and there's a search function. So it's super quick and easy to just put all the data in. Essentially, these forms that we're now quickly going through, this is something that you can, for a new data management plan, actually fill within minutes, if even, if you have the project proposal ready and it's something where the template already exists. Like for typical European projects. Well, license and access rights are license and access rights are had been actually set to the attribution, Creative Commons attribution. Not sure why they were kicked out now, but of course all these are available, and this is also how I published the data set. As said, there's one dataset input, so there's the template for Horizon 2020, since this was the basic basis for my project. And here I actually leave all the changes and head into the dataset. So these already are all the components that the data management plan for, in this case, the Horizon 2020 project must include. And so, of course, this is all readily available in the form, explains you what to go through. So from the title, I did not add another description since we only have one type of data set, and the overall description is already for the data management plan. So in the above level, so I did not add any more things here. And then you can see it guides you through all the input that these data management plans need. So from the purpose of the collection with all sorts of things, to the kind of formats. So as you saw earlier, we have formats that include construction details from the first work package where we built the devices. There's protocols for the experimental preparation of the samples. There's analysis files from spectroscopic devices. There's, of course, pictures from microscopes. There's all sorts of different other measurements in different kinds of files. And so I went through and specified all that was foreseeable and what kind of formats these should have. I should say in most cases, I did actually publish both the proprietary and the non-proprietary formats. This is including the original measurement files where we have, for example, for this microscope, the manufacturer-specific file, and I exported everything in readily available formats. I chose to divert for Excel files because, well, essentially also all the open source and free software can open the files that I provided. And by not exporting them into like a comma-separated value file, of course, I also made available all the formula and all the routines that went into the analysis. And so I found it useful to have these original files there published. There's a lot of descriptions. As you can see, we don't need to go to every individual detail, but you see that it really leads you through the whole process. Once defined what kind of data you have, it also asks how big the data is. So this makes you estimate, is my available storage space, is this enough, or do I need something else? And really leads you through the whole process. Yeah, of course, once you finish these, you have the data management plan ready. You can then easily upload it into the system. You can easily publish it and thereby fulfill all your requirements that the publisher has for you. And this does look like in a nice enough way to just use them as it is. You can directly also have a DOI and the license assigned. In this case, since it's the draft version that I exported, there's no DOI assigned. But you see there's a title page, all the essential information is there, and then it goes into the description. Now, at least for some of the building blocks that I put in, it doesn't export, it didn't export all the formatting all too well. So at least some of these data descriptions come out hardly readable. So the one that I then uploaded to Zenodo, I actually revised to have a nice structure that I liked. This was not necessary, but since I wanted to go a little bit further along the way, I decided that this is something I feel I was willing to do. So if we go back to the presentation, wrap this up with this very quick demo, you saw it's a super straightforward service to use, and something that's particularly beneficial to me using Argos over any simple like Word template or any of the other platforms that are available online. The tremendous benefit to me really is this sort of integration through the EOSC portal. So you have the direct integration with Zenodo. You can publish the data management plan directly there, get the DOI, you can directly upload this, you can directly extract out of the EU system all the funding information, and same for some other funders. And this whole integration into the ecosystem make things so easy and so straightforward that this was for me the way to go, and still is the main platform that I recommend to everyone using for these kind of applications. And overall, I think there's still some improvements that can be done, but I think it already makes it easier for you to conduct your research and handle your data properly and have everything ready. I think overall, already now, it does save you time to use this and create a data management plan. And with even more integration throughout the whole data management cycle that we saw in the beginning, this is really something that's super helpful. So this integration throughout the platform, that's the main argument that really sold it for me. With that, I'm done with my very quick overview with this quick demo case. And yeah, I thank you for your attention.
I just wanted to say thank you. And yes, if anyone has any questions, please feel free to ask. As we've already seen, all the projects that we're hearing from are using EOSC services, and these all have been integrated through EOSC, and we can already see the immediate impact of that on actual research. So I think it's really important to be able to see that and to see how practical it is for people already, even if EOSC as a concept is still quite abstract to a lot of communities. If no one has any questions, I think we can go on to the next use case from Laura Benassi. She's a technologist at CNR INO in Florence, Italy, and she's going to be talking about the Connect Gateway and interdisciplinary open science.
Thank you. Hi, everyone. I am Laura Benassi, and I am responsible for open science at my institution. And I am also the manager of the EGI-ACE NHS Connect Gateway. And this is what I will tell you today. Just for introducing, EGI-ACE NHS is a European project that is contributing to establish ERIS, the European research infrastructure for heritage science. Heritage science is an interdisciplinary domain of scientific study of cultural and natural tangible heritage. Heritage science draws on different humanities, sciences, and engineering disciplines. So our communities is really interdisciplinary. The other characteristics of my community is that we are a huge consortium. Our consortium is composed of 24 national nodes distributed across 23 countries around the world. And each national node is composed of tens of institutions and hundreds of researchers working in very different fields. So our characteristics are, we are a huge consortium and a very interdisciplinary community, which is the scenario. EOSC, the member in EOSC has really different approaches, different instrumentations, different methods to understand, interpret, preserve, restore tangible heritage. And this is one of the critical points. It's very difficult to maintain our community, our researchers, really updated on the latest publications, dataset, standards, software, because they are coming from different fields. For example, an art historian published on different scientific journals in respect of a colleague that is a chemist or a physicist. And so the art historian can miss some important information for their research on scientific result useful for the art historian. If you are studying Raffaello paintings, possibly you are interested also in the scientific non-invasive diagnosis, able to show the preparatory design and so on. Another point is to spread open science best practices inside our community, because each institution has its own open science policies, its own repositories, and so on. So it's very difficult. And we are also working on standards for interoperabilities because we are a very interdisciplinary community. Another critical point for us that is to monitor the impact of the EOSC on the global community of heritage science. This is because we are going to become a research infrastructure with a legal entity, and so it's important to define the impact just to improve our scientific strategy. Which is the solution? We met OpenAIRE and we obtained the Connect gateway. It is a really useful tool to unlock the potential for collaboration inside our community and also outside our community. The Connect gateway is able to enhance the discoverability of our research products thanks to a customized search engine. OpenAIRE created a targeted gateway with the collaboration of the EOSC, choosing specific repositories or the journals or the scientific journals where our researchers are publishing, or linking to the funders or the Zenodo communities. And so the Connect Gateway represents a secure place for EOSC community to publish results in a guided manner, following open science practices, and to showcase the research products under one branded in a unique entry point, the gateway. And this gateway can be set up in less than 1 month. At the moment, the EOSC gateway is in the beta version because OpenAIRE is developing an algorithm able to improve the data harvesting. What I get as a manager is very easy and user-friendly. I got an administrative dashboard where I was able to customize the description of the project, as you can see here, where I can include all the organization engaged in my project, where I set up the data sources where to catch information, so the journals where researchers are going to publish. And in this process, I got a lot of support from the OpenAIRE team. The portal can be customized, as you can see. Oh, sorry. As you can see, I insert also an image. I can choose also a graphic design. But what is important is that a user, a researcher in any field can search for our research products. Can be publications, can be research data, research software, or other research products like presentations or videos or communication materials. And user can check out the uptake of open science practices of the community. Here you can see that you can filter the results. For example, you can choose documentation in open access with a specific license, Creative Commons. You can choose different type of documentation, an article or a project deliverable, and choose also the field of science in which the information is. And what is important is for us is to deposit our research products in Zenodo. We choose this repository, and we created a community in Zenodo where we upload everything. Another key point, fantastic, is the possibility to link the research works among them. For example, if you publish a preliminary result of research, you can link these preliminary results to another scientific article that contains the final results of the research, or you can link with the funders. So it's very useful, and it's help the researcher to save time. When you upload a publication or a research data set in Zenodo, you have the link, direct link with the funders. And so you don't have to upload again the same documentation, the same data set in the funding and tender portal. So this is more or less what you see. I don't show you precisely because it's very, very easy. It's enough to go to the website and try. You can get many information on our research products. So, as I said, the EGI-ACE chess community is composed of chemists, physicists, conservators, art historians, archaeologists, paleontologists, and all of them have very different backgrounds. They publish in different journals and have specific repository for depositing data set. What was useful for EGI-ACE is the collaboration with OpenAIRE and EOSC, and we started to deposit the research products in the EGI-ACE community in Zenodo, and this helped our community to upload the metadata in a fair way and all the information in a fair way and in a homogeneous way. Another advantage is for the researcher is to maintain the ORCID profile automatically updated, because you can add the publication in the Connect gateway directly to your ORCID profile. And as I said, you can link the research product directly to the funders and to the projects. And you can also link, if you publish a scientific article with different acknowledgement of different projects, you can link to all of them. And another advantage is that we have the research product directly harvested from OpenAIRE, so included in the Connect Gateway and the EOSC Marketplace. And then all the documentation, all the research products are available for all. Which is the impact on being in EOSC and using the OpenAIRE tools. OpenAIRE services are part of the EOSC portal services, and EOSC NHS and the Future ERIS too. So it's very useful to be so connected. The OpenAIRE Connect and the EOSC are increasing enormously the discoverability of EOSC NHS and ERIS services and research outputs. EOSC NHS and ERIS offer digital services, but mainly hardware services. We open our facilities for researchers interested in doing non-invasive analysis. And Connect answer perfectly to the need of the community to make easier data curation and also data interoperability, due to the fact that we are so interdisciplinary and the researchers collect data in a very different way. Connect allows monitoring the impact of the EOSC NHS and ERIS community on the global community of heritage science. As I said, EOSC NHS has some partners, for example, in Brazil, in Peru, in USA. So it's very important that all these partners can stay updated on the research products of the project and to share with the community. The wishes for the future are already here. We are so enthusiastic of the Connect Gateway that we are working together with OpenAIRE, and we are curating a new gateway focused on heritage science, so more generic, that will be the legacy of the EOSC NHS project to the global heritage science community. The collaboration with EOSC and OpenAIRE is supporting our researchers to practice open science, to monitor the impact of our research on the global community, and most important, to share the knowledge with the broader community. This could mean innovation, new collaboration, and it is so important for our community. More or less, that's all. Thank you.
Thank you, Lara. I think we can I had a quick question based on the presentations. Anne mentioned this in her presentation, that open science in terms of performance and quality isn't just about the infrastructure. And I was hoping if anyone who's spoken so far during today's session would like to weigh in on that in the context of EOSC. Sorry about that again.
Yes, thank you.
Again, talking to nothing. Sorry about that. Yes, I actually wanted to jump in and ask a quick question to everyone who's spoken so far during the day, but it's something that Anne mentioned during her presentation. It's open. She said that open science in terms of performance, but also quality, isn't just about the infrastructure itself.
Exactly. Yeah.
I wanted to know if anyone wanted to weigh in on that, elaborate a bit more on the demos that they presented, and also just in the context of EOSC.
We are working with the OpenAIRE to develop also the monitoring tool. So for us as a research infrastructure, it's really important to have this tracking in any way, also because we are an ESFRI research infrastructure, and we have to respect some key performance indicators. So it's very important for us to track these also on open science practices. But I don't have anything to show you at the moment.
And this is the mandatory that you mentioned.
Sorry, Actually, my presentation will be all about open science in practice because I am a researcher. So I'm using the services and I will show how I use the services developed by Reliance and that are already present in the EOSC to do open science.
Great. Well,
in the demo, hopefully, if the services will work.
In that case, yes, let me introduce Elisa Trassati. She's a senior researcher at the National Institute of Geophysics and Volcanology in Rome, Italy. And she'll be presenting use case on geohazards.
So good morning to everyone. Yes, my presentation is all about using the EOSC services in my field, in my community, the geohazard community. So to manage and preserve the research work, make it available and discover new knowledge. Just briefly, the Reliance project is contributed to the EOSC exchange with a set of services for open, efficient management of the research lifecycle in support of fair and open science. So the services are here on the right. You know them already. So first of all is the research object concept and the raw hub to manage the research lifecycle. So the research object management platform. And then the Advanced Geospatial Data Management Platform, ADAM, to enhance the discovery and access of large amounts of data, in particular Copernicus data, and also the AI-based text mining services to extract relevant knowledge from scientific context. This is an overview of all the services because all the Reliance services are already onboarded in the EOSC marketplace, while the Reliance services integrate and rely on different EOSC core and other EOSC exchange services. As you can see here, Argos was presented by Sebastian, for example. So we saw many of these services, OpenAIRE, etc. We saw them before. So I am part of one of the three communities, the geohazard community, Anne, that presented before. She's from the climate change, and then there is the marine community also as part of the demonstrators of the Reliance project. So my community deals with the volcanic risk management cycle. So we are interested on the volcanic hazard definition before an eruption, to prevent the consequences of large eruptions. And also, of course, we are interested on the emergency phase. So when a volcano is erupting, for example, you see here the volcanic plume. Today, yes. This is an overview of the demo. I'm going to a live demo. I'm going to do it right now. So I work on the pre-eruptive phase. So what we call when a volcano is on rest. So it's showing activity, but it's not erupting. And typically there are surface deformations that we can map by satellite. Sentinel-1 in particular from the European Space Agency is commonly used, and these images must be processed. So I am able to collaborate with other researchers using the raw hub because my collaborator, Christian, processed a large amount of data, of SAR data, over the Askja volcano in Iceland, which is active in arrest, so it's showing deformation. So, but I'm able to discover his results that are fully documented in a research object, but I am also able to check the dataset he used for the processing by checking it in the Adam platform using the EGI check-in in order to log in very easily. Then what I want to do some modeling of this deformation, because the surface deformation is caused by the magmatic chamber, which is inflating. So I want to model this data and to find out the parameters of the deformation source. So what I do, I want to look for others' work, others' research on the modeling, and I can do it in the EOSC search, explore. So searching there, what I found, because I know that another volcano, Santorini volcano, has been studied. So the deformations at the Santorini volcano detected by SAR has been modeled. So this work by another collaborator, another researcher, Mikhail, has been documented in a research object. And I see here a nice, I don't know if you can see my mouse, this tag is telling me there is a Jupiter notebook. Here it is. So what I can do is I'm able to open it in the EGI. So I have the notebook and I have my data, which with some post-processing from the results from Christian, I have the input for the code. The code has been shared in the EGI. So I'm able to do my work to study my volcano in Iceland. So let's try to do everything. So first thing to do, I don't need to log in if I want to check others' works in RoHub. So here is the research object by Christian. He's able to fully document his work. I can see an overview here, or I go to contents. Here is with the bibliographic reference. Here is the data set, which I can download. And I'm interested on the original data he has been used. And you see here, I can open it in the Adam platform, but I have to log in this case. So let's log in. Let's sign in. Okay, I'm logging in with my ORCID. I did it before, that's why it's not asking again. Okay, now I can open it. Also here, I have to sign in. Okay, so here is the data set. So he has been using the Sentinel-1 interferograms. Here it's a part over the data set over Iceland. I can check some other dates, for example, here, and to check this. This is actually, it's not easy to understand, to read, because these are interferograms that must be processed and analyzed with quite a long chain, but I can, for example, check. So this is the difference of phase. And so Aschia volcano is this one here. And okay, and I have here all the data set in Adam for all the volcanoes in Europe. So for example, I can go to here, another date, whatever, this one. And I should have also the volcanoes here. Vesuvius and, yes, they are covered, Vesuvius and Campi Flegrei. So Okay, so here is the data. And what I want to do now is to, sorry, I cannot see because of the top. As I was saying, I want to discover others' work related to the modeling of volcanoes. So I go here, I search for Santorini and modeling, others, other results. Okay, so this is interesting. It has a Jupyter notebook, so I can go and discover it in RowHub. It is also fully documented, this work with the publication and everything. It has the input, output, so in theory, I can reproduce his work. Well, in the last months, the RowHub platform has been updated. It assesses also the completeness and the fairness, for example, with a lot of tools here, the enrichment based on the text mining, so several new tools, interesting tools. Okay, so I could fork this research object in order to do my new work here. So by forking it, it creates a copy owned by me, and I can update, change, substitute, delete all the resources and customize for me. So, but now let's go to the notebook. So this is the notebook which I can download, or I can open in the EGI notebook. This is what I'm going to do. Let's hope it's working. It opens the environment on the fly for me. Takes a moment, but it's coming. Okay. Okay, so here is the notebook, the original notebook on Santorini. So first of all, we want to save it with a new name on Aschia volcano. Then we can do some changes, of course, necessary changes, because now it's not on Santorini anymore. And okay. All the libraries to be installed. And okay. What I want to show you here, the code is stored in the data hub of the EGI. And I can actually go and check this, because this is shared for the community. So I can go in the data hub of EGI. I am already logged in, but as usual, you log in with the EGI account. And it's not here, is Reliance, this one. And from data here, there is all the resources shared by the community, and here is the VSM code as linked here from the data hub, and also the okay, so also the input file. In this case, I can even change it, because now I have my new data set, which is here. I simply link, what did I link? I'm working here in the shared area. So I have this one in the input. I simply link the PNG of my data. So just a few changes from the original one. I don't have the GPS, so I can go. Here is the setting of the model. Oops, sorry. Sorry, it's here. Okay, let me just check if I change it the, no, wait, I didn't change this one, sorry. Again, okay. So after the definition, I'm ready to launch my inversion from here. It is running. The zone is 28. So I'm doing the inversion of the geodetic data from detected by INSAR, by Sentinel-1. Here is how the inversion was going. Here I have the samples, the sampling of the inversion. Here is the marginal probability of my parameters. So if I'm happy with my results, I can, first of all, I can plot, here is the inversion. So this was the original data. This is the model and the residuals. If I'm happy with my results, I can copy everything in the shared area of EGI. Here, this one, the results, and I can also copy the tool, which is, how did we call it? ASCII insert. So if I go here, I adjust one. Oops, sorry. Now I should have all my results copied if I did it properly. I'm sorry, I copied it here in the ASCII EGI. Yes, so everything is here. Sorry. Why I cannot find it? Probably I didn't do it. I did it too quickly, sorry. Well, anyway, I just have to run it again to copy them. Because I copied it in Santorini, sorry. I didn't change it properly, but they are. So I copied everything in the wrong folder, but everything is here. I copied it in this folder here. Yes, right now, and everything is here. So this is what open science means to us. I was able to take someone else data, and also to work in a common, in a cloud in which I found others work, others results, and I was able to do my work and to share it with my collaborators and with my community, within my community. So I think I can, yes, stop here. And thanks for your attention. This was the last presentation of today, so thanks for waiting until the end.